next one we want to look at is an exponential function, and I want to look at number 22, e to the negative x squared. Let's call the function f e to the negative x squared. So I see it's an exponential function, or at the very least, the exponential function features in there. But because of the square, I really am not sure what to expect. I'm used to thinking that I don't have symmetry, but the square's presence might change things, and it's okay to not really know. I might have some horizontal asymptotes, I could say, but until I get to those steps, I really don't know for sure. Y-intercept I can do. Plug in 0, I get e to the 0, which is 1. So that was pretty straightforward, to the point where we can go and put it on our graph. Feel good about the graph, get something going, why not? Let's see what we can do here. Oh, not a square, that one. Let's put something on the graph, build some confidence, get some momentum. There it is, 1. I got something. Next up, asymptotes. Asymptotic behavior. Where I want to see, are there any asymptotes? What is happening? Alright, so I want to know if x is going to infinity, what is happening to my function? Well, a good rule of thumb is whenever I see a negative in the exponent, I can rewrite it. And that reminds me, ooh, there's a denominator happening, and that might allow me to do certain things and just see it in the right way. So now, if I look at the form of this limit, we look at just how the numerator is behaving. 1, doesn't change. Just how the denominator is behaving. And with a positive exponent, it makes it a little easier. So I know it's e to the something. If that's something, how does that something behave? Well, if x gets really big positive, x squared gets really big positive, so e to the something gets really big and positive. And therefore, the limit is 0. On the other hand, I have to also look at the limit as x goes to negative infinity of this function. Form of the limit gives me an indication of how the pieces interact. It's going to be 1 stays 1. Now it's e to the something. As x gets big negative, x squared gets big positive. So I have e to the something, where the something gets big positive. So I have another 0. So we'll write it over here. I have a horizontal asymptote on both sides, the line y equal to 0. Do I have any vertical asymptotes? That can only happen with the exception of a log function being present, where the denominator equals 0, but e to the something is never going to equal 0, so there are none. So let's put it on my graph. I have a horizontal asymptote, and I'm not sure how I'm approaching it. Leave it open because I know the next step is going to show it automatically. There's no need to worry about that here. So we made some progress. Step 3, we want to look at increasing and decreasing behavior. And for that, we need to look at the function, its derivative. But I want to look at the function in the most convenient form. I'm not going to look at this guy and do a quotient rule, especially not coming out of my previous rational function. I'm kind of done with quotient rules unless I really have to. I'm going to look at this version, because taking the derivative of an exponential function with a chain rule is not so bad. So, looking for the derivative, it's e to the something. So the derivative is e to the something times the derivative of that something. And then I can clean it up and put the negative 2x in front maybe. That looks kind of nice, like so. Now again, I see I have a negative exponent, so it might be useful for what's coming up to see it in its fraction form. Not necessary, but it's helpful sometimes. Then my two checks require that I look at when the derivative is equal to 0, when the derivative is undefined. When is it equal to 0? When the numerator equals 0 and therefore x equals 0. When is it undefined? It's going to have to be when the denominator equals 0, but because it's e to the something, that is never going to happen, because that's never equal to 0. So I have one contender. Let me just clean up my equal sign here. There we go. One contender to be a critical point. I'll make my table. Now you could actually decide at this stage, is this a critical point? Do I have a y value corresponding to x equal to 0? Yes, I do. It was the x-intercept. It's 0. So that is immediately a critical point. It's in the case of inflection points where I need to check the table and the concavity has to actually change. In the case of critical points, it doesn't matter. If it comes out of this and there is a point, it's a critical point. Now I have some pieces. I can make my table, but my table is only split at x equal to 0. I have a negative 2x. I have an e to the x squared. Together they give me the first derivative. Split it up over here. 2x is 0. When x is 0, it's in the numerator. Makes the whole function 0. E to the x squared is never 0. In fact, it's always positive, because I know what the shape looks like of e to the something. Negative 2x is going to go positive to negative. Now, by way of multiplication and division, two positives will make it positive. Negative and a positive will be negative. So I have an increasing section, 0. Whoops, let's make it nice and horizontal. 0, negative. So I see my little crest shape. Let's finish it by writing our sentences, maybe over here. F is increasing on negative infinity to 0. Should I include the 0? Yes. Function's defined at 0. F is decreasing on 0 to infinity, including 0. So what can we put in our graph? Well, this tells me what arrows are happening. Can't be this guy, because I am increasing. Where's turn off my eraser? There we go. I have a little cup here, and then I'm decreasing. So it can't be that bottom guy, because I'm not turning again. Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.